I'm going to show you two ways to come up with the approximation of the binomials. Well, no, the binomial series isn't an approximation. The binomial series is an approximation of something like 3 plus 2x to the minus 3, something like that. And it's an infinite series, it goes on forever. It's any point at which you stop before infinity. This equals is not true, it's an approximately equal sign. And because it goes on forever. So if you stop before you get to forever, which I'm assuming you will, then you don't actually have the same thing, you have something which approximates it. So I'm going to show you two ways, one of which you've probably seen, the other one you probably haven't seen, and then you can choose which one you like best. One is to use the formula in the book, which is probably what you're familiar with. So the formula in the book says that 1 plus x to the power of n is equal to 1 plus nx plus 1 over 2 factorial n minus 1 x squared. We'll probably just leave it there, plus dot dot dot, that's enough terms. And then there's some more terms on the end. So the next one, the coefficient would be 1 over 3 factorial, and then there's three things after it, n minus 1, n minus 2. And then down the line somewhere you might have 1 over 7 factorial with 7 things after it, n minus 1, n minus 2, n minus 3, n minus 4, n minus 5, n minus 6. Okay, so that's the formula in the book. We can't use that directly on this expression because of the 3. So the 3 needs to be pulled out the front. Now, this is where things start to go wrong. Problem number 1 that occurs is that 3 comes out without its power. So when 3 is in this bracket, everything in this bracket is under the influence of minus 3 as a power. So when the 3 hops out, he can't just ignore that power that was on him. That power comes out on top of him as well. So that's mistake number 1 that happens. Mistake number 2 that happens here is that the 2x term doesn't get divided by the 3. Or whatever's on its way out. So whatever's on its way out of the bracket needs to be divided under here as well. So that's another mistake that happens. And then we move forward, which is where another mistake happens. So what happens now is that students just work on this because they know that this matches this and they can use the formula on this. So they work on this, subbing all the things into the formula, simplify, simplify, simplify. And this little guy, he gets totally lost. He's gone. So this is another common mistake, is that 3 to the minus 3 or whatever popped out the front just disappears at some point down the page. So I will make sure he has not disappeared by writing him like that. Okay, let's use formula 1, that matches up. So 1 plus n is the power which is minus 3, x is the second term which is 2/3 x, plus half n is minus 3, n minus 1, and then x squared. Now, that's where we get the next mistake. So, mistakes that happen here, the main one is that 2/3 x squared, this bit here, is written as 2/3 x squared. Very, very common to see that. And then that means that it's all going to go horribly wrong. Right, now we start to expand out. Sometimes this is where the 1 over 27 disappears, can disappear at any point. And then we get 1. Now, at this stage, what happens is students go boom to the end. They go way too fast and they go, just calculator it, write it all down. They go too fast, some minus signs go missing. The 2/3 doesn't get squared and the answer comes out wrong. So I'm going to go a little bit more slowly. I'm going to go minus 6 over 3 x. Now I've got a plus here because 2 minuses. And I've got 12 divided by 2, which is 6. And then I've got 2/3 being squared, so that's 4 over 9, x squared. And now I'm going to expand it all out. So it's going to give me 1 over 27 minus 2 over 27x plus 8 over 81 x squared. And obviously this does, if I don't put plus not, that's a lie, because this actually does, this is true, that does equal that. But that's not true because it goes on forever. Now the equals are true. So, last thing that goes wrong, going too fast at the end. Causes little slips, as always, and that goes wrong. So, an easy technique, full of potential areas for problems. Right, see what you think about this instead. Now I like this one because it means that you use exactly the same method whether or not you're doing an actual expansion, 3 plus 2x to the 10, or whether you're doing an approximation, 3 plus 2x to the half or the minus 3 or something like that. And what you do is you make a table and your first term, 3, goes in the top column and your second term, 2x, goes here. Or rather, this is the one that's going to be in increasing powers of x. No x's, x to the power of 1, x to the power of 2. So the thing we want the increasing powers of, that goes in the second column, but to be honest, it's usually in the second position, so that's not very difficult. And then we have a column for the coefficient n choose r that's at the front. Okay, now, exactly the same as when you have 3 plus 2x all to the power of 7, say, what is happening is that the power is transferring slowly over from one of the terms to the other term. So this term gets all the power to start off, all of it. This guy gets nothing. And then as we go through the expansion, the 3 gives over one of those powers slowly, one at a time, to the 2x. And the same sort of thing is going to happen here. So 3 is going to get all of the power, all of it. Now 3 is going to get 1 less power. And then 1 less power, and then 1 less power, and 1 less power forever. Meanwhile, 2x, this is the thing we want the increasing powers of, 2x starts off with nothing, no powers at all, and then he's allowed 1, and then he's allowed 2, and he has more and more and more as we go across. In front of each of these terms, there's your binomial coefficient, which tells you the number of ways that you could create this combination when you're doing your expansion, and these are exactly the same as the coefficients here, of course. So the first one is always a 1, the second one is always n, which in our case is minus 3, then the next one is 1 over 2 factorial, then n minus 1. So you can see it here, it is a half n minus 1 is there, there's the minus 3 here, there's the, well, we didn't write the 1. So it's exactly the same ingredients, but the layout here is really nice and clear. And then all you need to do to create the expansion is just multiply these 3 together to get the first term, multiply these 3 together to get the second term, multiply these 3 together to get the third term. So what do we get? 3 to the minus 3 times 1 times 1. There's a minus there, no more minuses. Then we've got 3 to the minus 4 times 3 times 2. X's. This one's going to be positive because there's only 2 minuses. And then we've got a 6 here, 12 divided by 2 is 6. We've got 6 here, 6 divided by 3 to the power of 5, and then times 4 because it's being squared. Okay, now, totally up to you. I think that is cleaner, easier, and simpler to use and less likely to go wrong. It avoids loads of these little problems that occur, but it is completely up to you. You can even do both ways to check your answer if you wanted to. Now, what about the set on which this is valid? So you cannot have a series that goes all the way to infinity, up and up and up, and you're just adding on and adding on and adding on and adding on in infinitely many terms for infinite amount of time, because you will get infinity, unless this term is shrinking so fast that even though there's numbers in front of it, the shrinkage caused by this thing getting tiny, tiny, tiny means that the bit you're adding on gets smaller and smaller and smaller so fast that you do actually have an upper limit. So you have like an asymptote. As you add on, you are getting bigger because you're adding on, but you're getting bigger in a smaller and smaller and smaller way, and there's an asymptotic long-term growth towards an actual value. So it is important to know when they're valid, and if I just put this at the end, you can see easily with this one when it's valid. The thing that you are putting the powers on, the 2/3 x, so that would be 2/3 x cubed, 2/3 x to the 4, etc. That, the modulus of it, must be less than 1. So this must be between -1 and 1, and that is because if we have something between -1 and 1 and we keep putting powers on, then it gets smaller and smaller and smaller. Now here, even though this was simpler, it's less obvious to see where this is because we didn't have to do that division to get the 2/3 x. So you would need to remember with this method that the thing that needs to be less than 1 is this divided by this. So you would have to remember that extra step, that 2x, maybe I'll put it here, 2x over 3. So this is this term divided by this term. The modulus of that has to be less than 1 in order for this to be valid. I'm just going to change the colour of this. I did not like it, it's too much red. So the top is on this, the wrong way round, isn't it? Maybe that's a good way to remember it. It's the wrong way round. It's the 2x is on the top and the 3 is on the bottom, and this divided by this, modulus, has to be below 1. You could also just look at this and think if I was doing it the formula book way, I would have pulled out a 3 and I'd have 2/3 x here. So it's 2/3 x that needs to be between -1 and 1 for this expansion to work.